Yeah, okay. Thank you, Vishnu. A very good morning to all. In in today's class, we'll be seeing the syndrome calculation. First of all, I'll give you a recap of what is this syndrome that we had seen in previous class. So this syndrome is used for error correction. So as you had seen the property, this syndrome decoding is used for error correction. For example, if you have an 7 comma 4 block quotes, 7 comma 4, which represents n is equal to 7 and k is equal to 4, we'll be having 4 information bits and 3 check bits. So altogether we get 7. Okay, so let us assume that here is your syndrome decoding. This syndrome decoding is a method to correct your errors in block codes. X is representing your transmitted vector, Y is representing your received vector. If X and Y are same, there are no errors. If Y is not equal to X, then it shows that there is an error. Okay. So in order to find this syndrome decoding, or in order to find whether Y is not equal to X, we need to follow a procedure. So the procedure is that we need to first find H matrix. So H matrix is obtained by P submatrix transpose is to identity matrix. So this H matrix can be rewritten in the form of H transpose. Okay, the H transpose will be the transpose of the H matrix, which is being obtained from P transpose. So you can write that as an equation number 3.3.22 as HT is equal to P, everything in a single column. So transpose is changing your rows into columns and columns into rows. So of this size. Okay. So H transpose will be getting like this. So now the important property used in syndrome decoding is that always your X H transpose should be 0. Okay. X is your information which consists of message M as well as check bits C. If that is equal to 0, then we can state that that code word doesn't has any errors at all. And if XH transpose is always 0, we can assume that in the transmitter part there are no errors. Where do we get errors? Mostly is that we get the errors only in the receiver part. So at your receiver, we need to use the received code vectors. So the received code vectors are represented in Y. So YH transpose you should do. So if you do YH transpose and if you get everything as 0, it states that X is equal to Y, meaning there are no errors in the received code vector Y. And if YH transpose is non-zero, then Y will not be equal to X and there are some errors in the bits. So in that particular Y code vector, so that we need to find it. I think we had completed the definition of syndrome. If you had completed also, no issues, I'll give you a glance of that. So errors are present in the received vector, and if it satisfies this property, S is equal to Y H transpose, then it is the definition of your syndrome. It shows that if Y H transpose is non-zero, errors are present. And the next property is that if Y H transpose is zero, there is no errors. So this is what the definition of syndrome is. So we can write in the form of matrix also. S is equal to YH transpose can be written as S 1 cross Q is equal to Y 1 cross N H transpose N cross Q. Equation 3.3.27. So how do we detect errors with the help of syndrome? Is that if non-zero elements S are being represented as an error in the output, there are two possible cases. One is no error in the output, Y is equal to X, then it will be valid. And if there is an error, Y will not be equal to X. So this we'll see with an example. So consider X as this. X is equal to 1 0 1 1 0. Let it be a transmitted vector. Second, let Y is equal to 1 0 0 1 1 be a received vector. Okay. So see the difference in between the Y and X. How many bits are being errored? Can anyone able to see this and tell me? How many bits? I'll write it. X is equal to 1 0 1 1 0. Y is equal to so in the chat box you can see I have given two vectors, X vector and Y vector, and I'm saying you to find how many bits have been errored. So can anyone give how many bits are being errored? And you should indicate no, not 6. The total number of bits is 6. So not 6, it's 5. Total number of bits is 5. Then how do you get 6? 4. How do you say 4? See, compare X and Y. Compare X and Y. First bit is 1 1 as it is. Second bit 0 0 as it is. Third bit you see in X it is 1 but Y it is 0. So third bit, and next check fourth bit. What's going on here? Fourth bit you see, fourth bit is in X it is 1, in Y it is 1. So it's not error. See the fifth bit. In fifth bit, X is 0, Y is 1. So third bit and fifth bit, totally 2 bits are okay. Totally 2 bits are in error. So somebody had given the answer as 2. Yes, very good. Srija, Tanuja, very good. Pavan Chandra, Sri Vishnu, Surya Chandra, very good. So the third bit and the fifth bit are the errored bits in this example. Okay. So when we see this, we can easily find that these are the bits being errored. But how do we use and machine to calculate this? Okay. So we can write the errored bits as E is equal to 0, 0. The third bit is an error, so 1. Fifth bit is an error, so 1. So this is how errored bit E can be represented in terms of error vector. Now we will find this it easily. Okay, so use the modulo 2 addition of x and E. Do x and E modulo 2 addition bit by bit. First bit with the first bit, second bit with the second bit, third bit with the third bit, fourth bit with the fourth bit. Okay. Since in x we are having 5 bits, in y we are having 5 bits, and E also we are writing. If the bit is same, we'll be writing it as 0. On comparison, if the bits are different, we'll be writing it as 1. Okay. So now do y is equal to x modulo 2 addition of E. This and this. So write 1 modulo 2 0, 0 modulo 2, 0 modulo 2 0, 1 modulo 2 1, 1 modulo 2 0, 0 modulo 2 1. So do modulo 2 addition. We'll get 1 0 is 1. Next 0 0 is 0, 1 1 is 0, 1 0 is 1, 0 1 is 1. So now you see this. See this. So this is your y. Do we get y or not? Check it. Check what we had wrote here 1 0 0 1 1. We got it same here when we do x modulo 2 addition E. We can get y easily. Similarly, we can write x also as y modulo 2 addition E. So what is y? Y is 1 0 0 1 1. E is 0 0 1 0 1. So do modulo 2 addition. When you do modulo 2 addition, we will be getting obviously x. See here y and E. So 1 0 you get 1, 0 0 we get 0, 0 1 we get 1, 1 0 we get 1, 1 1 is 0. So this is how we can correct the errors by using syndrome principle. If the bits of error is being easily found out, then the correction is more easier. Just do modulo 2 addition of the corresponding bits with respect to your y. We'll be getting x. So any doubts in this? A simple concept. Let me check for any questions in the chat box, then we'll go for the next. If, for example, if the length of the x is 5, obviously the length of y also will be 5. And when you compare x and y, obviously we will get the error values of 5-bit sequences. Compare first bit of x and first bit of y. So that if it is having error, we'll be writing it as 1. If there is no error, we'll be writing it as 0. So in that way, we can calculate the length sequences of errors. How many number of bits are present in X will be equal to the number of bits present in Y, will be equal to the number of bits present in E also. I think I had clarified Tanuja's doubt. Is it clear? No, then can we calculate the length also in the same manner? An error and length. No, if X is having, for example, I'll write X is having 5 bits. Y is 5 bits. What about E? What about E bits? That is your question, right? Is this the question that you are asking? If, for example, X is 5 bits, Y is 5 bits, what about E bits? E is your error vector, X is your transmitted vector, Y is your received vector. Yes, Tanuja, is this a question? Yeah. Then if X is 5 bits, Y is 5 bits, E also will be 5 bits. E also will be 5 bits. If X, I'll write for example, if X is 7 bits, Y is 7 bits, what is errored vector bits? How many number of bits are there in errored number of bits? Can anyone give the answer for this? If there are X vector are 7 bits, Y vector are 7 bits, obviously our E vector will be 7 bits. Yes, very good, Shrikala, Harshita. The length of all X vector, Y vector and E vector should be same. That is the conclusion. I hope you would have understood now, Tanuja. Shall we proceed for the next? Okay, I'll proceed. We'll go. So the relationship between syndrome vector and the error vector can be obtained by S is equal to Y H transpose. S is equal to Y H transpose. Now simply substitute Y. Y is X modulo 2 addition E. X modulo 2 addition E. Substitute that. And now bring H transpose inside. We'll be getting X H transpose modulo 2 addition E H transpose. Then we always know that X H transpose is 0. X H transpose is always 0 from the property of syndrome. So we can calculate syndrome is equal to E H transpose. Hey. So we get the by the property of syndrome, we get S is equal to E H transpose. So this is the relation that the syndrome depends upon the error pattern only. Okay. And the syndrome doesn't depends upon the particular message. It depends only on the error. If error is there, we'll be calculating the syndrome vector. So if syndrome vector is calculated, we can easily rectify the errors. Okay. So let us see an example of that. I think we had seen this example already, I suppose. Yes. The calculation of syndromes we had done in previous class. So in today's class, I'll solve you a different problem based on correction. We had detected errors in the previous class. So now we'll see how to correct them using syndrome vectors. So an example is given with 7,4 block codes. The transmitted code vector is 1001110. This is given. See how number of bits? 1, 2, 3, 4, 5, 6, 7 bits are available. And see in the receiver, 1, 2, 3, 4, 5, 6, 7 bits are available. So now we consider that the third bit is error. Physically, by seeing, we can see that the third bit is error as it is being encircled. I am encircling that bit number 3 in the receiver is being errored. So encircled. So how do we do it? With syndrome coding, we will see that. Okay. The procedure adopted for error correction using syndrome decoder is that first we need to calculate S is equal to Y H transpose. We need to do Y H transpose. Then we should check the row of H transpose which is as same as S. And for the Pth row or the P matrix row of H transpose, we should see in which bit it is in error. So then we need to write that corresponding error vector, and we can obtain the correct vector by using this X is equal to Y modulo 2 addition E. Don't worry, all these 4 steps I'll explain with the same example. So first we will obtain S is equal to Y H transpose. So Y is given 101110. So write it. H transpose, recall from the previous example. Okay, the H transpose. I'll show you the H transpose. The H transpose is taken from this previous example. The same HT, you take it. In some problems, HT will be given. In some problems, we need to derive HT. So it depends upon the problem that you are solving. So in this case, I'm taking the previous examples, H transpose. So take that, which is having 101, 111, 110, 011, 100, 010, 001, which is having matrix of 7 cross 3. 7 rows, 3 columns. So recall that HT. So write it. See that both are same. Then do model to addition as you all are familiar. Do modular to addition. So this row with the first column, this row with the next column, second column, this row with the third column. So we'll be getting 1, 1, 0. So try to be familiar with how to do modular to addition. Practice it. So then, now we had found S is equal to Y H transpose. The answer is being found as 1, 1, 0. So this S is equal to Y H transpose is always equal to E H transpose by this definition. By this definition, S is equal to E H transpose. So we can write S YH transpose that we had obtained as EH transpose, which is equal to 1, 1, 0. So this is how to write syndrome. Yes. Now, after writing the syndrome, yes, we need to determine the row of H transpose, which is as same as yes. Okay. So now see what is this S transpose is. S is 1, 1, 0. Now go back to H transpose. So this is H transpose. See in which row this 1, 1, 0 is present. Can anyone give me the answers by turning on? Okay, can type in the chat box. S is equal to 1, 1, 0. Now this 1, 1, 0 is present in this H transpose. Can anyone say where this H transpose is present in this row?
Third row, sir.
H transpose, it is somewhere it is present. 1, 1, 0. In
Third
which
row,
row?
Third row.
Third row. Yeah, very good. Yeah, yes, correct. Third row. I'll type it in the chat box also. Third row has S is equal to 1, 1, 0. Third row has S is equal, sorry, third row is having 1, 1, 0. Okay. I forgot, I should write H matrix. In H transpose, yes, having 1, 1, 0. In H transpose, yes, 1, 1, 0 is found in third row. Then I'll proceed. It is found in third row in H transpose. So now make a note of that. So in the error pattern, we had found it as third row. So we can write in error vector as E is equal to all the bits in error should be 0 except the third row or the third column. Can write. Since the third row in the H transpose is an error, we can write in the error vector as the third bit to be as errored. So I'll write it as 1. If there is an error in your system, we can write equivalently to that as a non-zero element. So here the non-zero element is 1. Since it is in the third row, we can write it in the third bit. So the third bit is an error. So 0, 0, 1, 0, 0, 0, 0. Because the remaining others are non-errors. So the third row is alone your error, so third bit is error. Okay, understood this? Now, how do we obtain the corrected vector? Corrected vector formula is x is equal to y. We have I want to find the corrected vector. So x is equal to y modulo 2 addition e. So recall this formula. X is equal to y modulo 2 addition e. So write all the sequence of y, write all the sequence of e. So e is from here, y is as given in the question. So do modulo 2 addition. Now see, x is equal to, when you do perform modulo 2 addition, 1 0 0 1 1 0, which is as same as the transmitted code vector. Okay. So thus I can show you that a single bit error can be easily corrected using syndrome decoding. So any doubts in this? Only for single bit error we can correct it. Any doubts? If you're having, you can put in chat box. We had done 4 steps. One is we had calculated S is equal to Y H transpose, and we had found the syndrome 110. We had found in which place it is present. It is present in the third row. So in the error, I can write the third bit is an error. So that vector I'll be writing as terms of E. Then that I'll be doing modulo 2 addition with modulo 2 addition with y. So if you do, we'll be getting x value. So this is equally applicable for single bit error correction. You can see what is x? X is 1 0 0 1 1 1 0. So you can see that x is 1 0 0 1 1 1 0. This is error correction using syndromes. So this is single bit error correction. Now let us see for 2-bit errors. We'll check whether if there are 2 bits have been errored, there are 2 bits error, or if there are 2 errors, what happens? Now I consider third and fourth bit are in error. I consider, for example, I consider third bit and fourth bit are in error. Third bit and fourth bit are in error. I consider. I perform S is equal to Y H transpose. So I do, and I get the syndrome as S is equal to 101. Okay, but you see 101 101, which is obtained in S, it is present only in first bit. So here I cannot say that the error pattern will be 1 1 remaining all zeros. So this cannot be done using syndrome decoding. If more than 1 bits are being errored, we can detect, but we cannot correct using syndrome decoding. If we do that, we'll get a wrong value of x. Surely you'll get wrong value. If you want, you can try it. So in this case, what we do is that we'll be, if you get double errors, we'll be using an extension of the Hamming codes. If you want to correct double errors, we need to use an extension of the Hamming codes, which is adding one more extra bit to correct the double errors. That can be done by using parity. Okay, parity can be added. Okay. So we'll see a problem with examples. We'll be proving that also. For a linear block code, prove with examples that the syndrome depends only on error pattern and not on transmitted code word. And second, all errors that are occurring differ by a code word having the same syndrome. So these are some two proofs to be done. So we know that S is equal to E H transpose. So just now I had explained you how do we got S is equal to E H transpose. So this itself will show that S is dependent on only on error pattern, only on E, not on code word X. And second thing is that all error patterns that differ by a code word have the same syndrome. Having the same syndrome. So let us see how it is. So consider two vectors x1 and x2. We are introducing error. Okay, let us have two code vectors x1 and x2, and we are introducing error in the first bit. Okay, then I can write E is equal to 1, remaining all zeros. Okay, remaining all zeros. So then we can find the S1 value. S1 is your syndrome for code vector 1. We can write S1 is equal to Y1 H transpose. Y1 is X1 modulo 2 addition E H transpose. Then do multiply this H transpose inside. So X1 H transpose modulo 2 addition E H transpose we get. Since we all know that always X H transpose is 0, if it is applicable for code vector X1, then it will be X1 H transpose will be 0. So we get E H transpose. Similarly, we can do it for the second syndrome. Having code vector x2, for x2 we will be getting received signal as y2. So y2 H transpose, y2 can be expanded as x2 modulo 2 addition E. Substitute it here, we will be getting x2 modulo 2 addition E H transpose. Multiply this H transpose. Inside we get x2 H transpose modulo 2 addition E H transpose, and I said x2 H transpose will be 0. So you can see that S1 and S2 all will depend on EH transpose. So we can observe S1 is equal to S2 is equal to EH transpose. Thus showing that all error patterns that differ by a code word have the same syndrome. Syndrome is same for different code vectors. Okay. So this is a problem as well as a proof of statement. Next problem is that we are going to do a problem based upon the parity check matrix. We are having two code words. We'll see how to solve this. So let us see the parity check matrix. The parity check matrix is same as we had seen in the previous problem. H is equal to 3 rows, 7 columns. We take the same parity check matrix. In some problems, different parity check matrix also will be given. I'm using the same parity check matrix. So write it, parity check matrix as H is equal to 1 1 1 0 1 0 0 1 1 0 1 0 1 0 1 0 1 1 0 0 1. So for this parity check matrix, the question is given as two code vectors, x2 and x3 is given. X2 and x3. X2 is given as 0 0 0 1 0 1 1. X3 as 0 0 1 0 1 0 1. So here a gap is given between the fourth and the fifth. This states that there are M is having 4 bits, C is having 3 bits. Okay. This is an example for your 7,4 block codes. Message will be having 4 bits, which is K is equal to 4 and Q is equal to 3. So X3 is given as an example 0 0 1 0 1 0 1. Now in the question, I assume that the first MSB bit is error. So we introduce that first MSB bits in X2 and X3 are errors. So if there are errors, we should write the non-zero element in that place. So for Y2, we can write the non-zero element as 1, the remaining as it is. If we introduce first bit as error in X3, we get Y3. First bit is error, non-zero element 1, remaining will be as it is. So write it as it. So then let us calculate syndrome for each. We'll calculate syndrome for each. So syndrome is S is equal to YH transpose. So here we have Y2 and Y3. So 2. So right, we'll find it for the first S2. So S2 is equal to Y2 H transpose. Y2, just now we had wrote, here is Y2, 1, 0, 0, 1, 0, 1, 1. So right it is. H transpose is obtained from this H matrix, transposing of this. So we can write this matrix. So when we do modulo 2 addition, we get syndrome of S2 as 111. We get the syndrome or the S as 111. Now see this S2, which is 111. See in the H transpose matrix, in which row it is appearing? Can anyone unmute your mic and say in which row it is appearing? S2? Nobody is. Let me see in the chat box.
Sir, first row, sir.
First. Okay. First is correct. Okay. So keep it as it is. Make a note, it is the first row, that's all. Now, similarly, we calculate the syndrome for second code vector. So the received code vector will be y3. So y3 H transpose. So y3 is here. Y3 is here. Do it 1010101. So take it, write it here. H transpose is here. Do modulo 2 addition. We get S3 as triple one. You will get triple one. Check it. You obviously will get S3 is equal to 3 ones. Now see for S3. S2 you had said that it is in the first row. Now see the same for S3 also. S3 is also appearing in S3 is equal to again triple one is also appearing in first row of H transpose. Yes, as you said correctly, yes, it is first row only, right? So first row. So then whatever might be your code vector, see both the code vectors, received code vectors are different. Though the code vectors are different, the syndrome calculation which we had done is that we had assumed first bit to be as first MSB to be as error. So it has identified that the first bit is error using syndrome decoding. So this proves that for a particular error pattern, syndrome is same. The particular error pattern represents that we had taken first MSB in this case. If you take second bit in another case, also will get same syndrome pattern. So thus the conclusion is that this proves that for a particular error pattern, syndrome is same even if the code words are different. Okay. Any doubts on this? Okay. So the next topic is designing a syndrome decoder for linear block codes having n comma k. So this diagram will show you an diagram of how the syndrome decoder is present. So we know that S is equal to YH transpose. So we require a block of that. And HT is stored in the syndrome calculation always. So HT is always present in the syndrome calculator. And always the circuit for this decoder can be drawn as such is that we need to do Y and E. Y modulo 2 addition E. So which is our X value. X is your code vector that is to be transmitted. Sorry, that is to be retrieved, not transmitted. That is to be retrieved at your receiver. So X is to be obtained. So the received code vector is Y. Received code vector is Y. We are going to do modulo 2 addition with E. Okay. So E is present with bit sequences E1, E2, E3 till En. Okay, with Y. So Y is having Y1, Y2, Y3 till Yn. So everything should be done modulo 2 addition. Every bits. First bit, second bit, third bit, fourth bit till nth bit. All should be done modulo 2 addition. So I put a diagram of modulo 2 addition symbol. And where do we get this y? y1, y2, y3 till yn is that from the receiver. From the receiver, we get y signals. So y is given a fed to your y1, y2, y3 till yn. So y is coming from your receiver, received code vector. So how do we calculate this E? Is that E is obtained by doing S is equal to Y H transpose for every bits. Okay. S will be obtained from Y H transpose. H transpose will be always present or will be present inside your syndrome calculator. The syndrome calculator will be having your H transpose. So Y is obtained from y1, y2 till yn is obtained from y. So those are being manipulated using syndrome calculator. Thus they will produce S. In turn, we can find up the errors. We can find out the errors which can be written as a lookup table for error pattern. So which bits are being error. So that information is given to the error vector corresponding to S. So E1, E2, E3 till En. So when we do modulo 2 addition of this, we get x1, x2, x3 till xn. So thus we can get the corrected code vector as x is equal to y modulo 2 addition E. So this is the syndrome decoder block diagram, or this is how we construct a syndrome decoder for linear block codes. Next, we can use maximum likelihood decoding also, such that we get errors to be rectified where errors are more than 1. The syndrome decoder is optimally used only for correcting errors, for only single errors. If there are only one error being produced, we can easily correct by this. So if you want to enhance and if you get more than one error to be rectified, we need to obviously go for some other extended codes of Hamming codes. Like for example, we can go for maximum likelihood decoding that can be implemented. So which is out of our scope now. Okay. Out of our syllabus. We need not concentrate on the maximal likelihood decoding. Okay. So we'll see an example. We'll see an example as how to construct a matrix by the diagram. We have drawn in syndrome decoder diagram. How to construct a generator matrix. How to find H transpose. How to determine the error capabilities. How to prepare a suitable decoding table. Then how to decode the received vectors. சொல்லுங்க மேடம் கிளாஸ்ல இருக்க மேடம் சொல்லுங்க மேடம் காலேஜுக்கா மேடம் இல்ல காலேஜுக்கெல்லாம் இல்லை மேடம் வீட்டில் இருந்தேதான் இல்ல சொல்லுங்க மேடம் நான் மியூட் பண்ணிட்டேன் ஓகே ஓகே மேடம்
நீ வந்து ஸ்கேன் பண்ணி அனுப்பு.
Yeah, sorry for the interruption. So the problem is for a systematic linear block code, we are having some parity checks. So there are some 3 parities, C4, C5, C6, that we'll see how do we calculate that. We need to calculate how to construct a generator matrix, how to obtain H transpose matrix, how to determine the error correcting capability, how to prepare a suitable decoding table, and we need to decode the received vectors. Sorry, yeah, received words or vectors 101100 and 000110. So this we need to decode. So from this question, we need to understand what are this. So when you see the question itself, it shows that there are 1 2 3 4 5 6 bits. See this received vectors. Received vectors are 1 2 3 4 5 6. There are 6 bits of information of y. If y is 6, always x is also will be 6. Errors also will be having 6 bits. Okay, and they are given specifically that the check bits are C4, C5 and C6. C4, C5, C6. So out of this 6 bits that we write information, the last 3 C4, C5, C6 are your check bits, and the remaining first 3 bits are your data bits or your information. Okay, so how do you get this C4, C5, C6 is that in the question that given C4 is obtained by modulo to addition of D1, D2, D3, C5 as D1, D2, C6 as D1, D3 modulo to addition. So now write that instead of x1, x2, x3, here the given question is D1, D2, D3. So that is the only change. Remaining all is same. So D1, D2, D3, right? And write the P submatrix. P submatrix is obtained by from the question. Here in the question it's not given. So now we are going to generate. Okay. So since it is 3 cross 3, since the check bits are 3, it is 3 cross 3. So P11, P12, P13, P21, P22, P3, P23, P31, P32, P33. Now do modulo 2 addition. So C4 can be obtained as D1, P11, modulo 2 addition D2, P21, modulo 2 addition D3, P31, D1, P12, modulo 2 addition D2, P22, modulo 2 addition D3, P32 for C5. For C6, we get D1, P13, modulo 2 addition D2, P23, modulo 2 addition D3, P33. Now, compare the above equations, these equations, with the parity matrix. With the equation this. When you compare, okay. So how do we compare is that in the place of D1, we have a value. In D2, we have a value. D3, we have a value for C4. So put 3 ones. In C5, we have only value for D1 and D2. So put against D1, 1 against D2, 1. D3 is not there. So put 0. So see here, D3 is not there. So put 0. Now for C6, D1 and D3 is there. D2 is not there. So first for D1, 1, for D2, 0 and D3, 0. So thus you will be getting this parity matrix P. So any doubts in this equation 3.65? Because obtaining this P matrix is an important. From this P matrix, the remaining is all familiar to you all. You can easily determine the generator matrix. From the generator matrix, H matrix. From H matrix, we can obtain syndrome. From syndrome, we can easily retrieve our Y, which is your Y code word. So any doubts in this P value obtaining? Let me check in the chat box. Kindly check this equation 3.362, compare that with 3.364. Wherever you have the presence of D1, D2, D3, it should be given as 1. If there is no presence of D3 in C5, it is to be 0. Here in C6, the presence of D2 is not there, so it is 0. So remaining will be getting like this. So I'll give you 2 or 3 minutes for checking this such that you can easily find P value easily. If P is found, remaining is all easy. So kindly see this. If you have doubts, put in the chat box. So after determining P, we can easily find G matrix, which is the first question to obtain generator matrix or construction of a generator matrix. Generator matrix is always Ik is to Pk cross Q. So K is 3, we had found. So identity matrix is your I. So 1, 0, 0, 0, 1, 0, 0, 0, 1. So P, just now we had found, write it as it is. First row 1, 1, 1, second row 1, 1, 0, third row 1, 0, 1. So then after finding generator matrix, our aim is to find code generated. Okay, finding the individual code vectors or the code words. So how do you find the individual code vectors or code words? We have done already some 2 or 3 problems like this. Same, we need to write the message vector. Message vector is 3 bits of information. So since there are 3 bits of information, we'll be getting 2 power 3 as 8. So there are 8 sequences, D1, D2, D3, 000 to 111. We need to write in sequences 000, 001, 010, 011, 100, 101, 101, 110, 1 1 1. So for this, we have check bits as 3. 3 check bits are C4, C5, C6. C4, C5, C6. So how do we find C4? C4 is D1, D2, D3. All the 3 bits modulo 2 addition. So C4 we get. Similarly, C5 we get by doing modulo 2 addition of D1 and D2. D1 and D2. Next for C6, D1 and D3. So do modulo 2 addition of D1 and D3. So we'll be getting C4, C5, C6 for all the 8 code vectors. For all the 8 code vectors. Then write the code words or the code vectors by combining D1, D2, D3, C4, C5, C6 in sequence. Write it in sequence. So this will give you code vectors for first serial number. For the second sequence, perform the same procedure as we had done for the first serial number, third serial number, fourth serial number, fifth, sixth, seventh, eighth. For all, follow the same procedure. After completing the code vector or code word, which is our transmitted vector X, just simply determine weight of that particular code. And you all are familiar, how do we find weight of each code word or each code vector? The number of non-zero elements in the code vector. The first one, 0. Second one, non-zero elements are 3. Next one, 3. Next one, 4. Next one, 4. Next one, 3. Next one, 3. The last one is 4. So this is how do we find code vectors and the corresponding weight of those code vectors. Next is to find the error. Let us see the question. Third is to determine the error correcting capability. The error correcting capability, as we had seen, is D minimum should be greater than or equal to S plus 1 is the formula, or is the format for finding error correcting capability. Now, from the weight of the code vector, find the minimum weight of the code apart from the non-zero element. Okay, but from the first, which is always 0, no information which is being sent. Since there are no informations in all the 3 bits, check bits informations also will be 0. So the weight of the code also will be 0. So this we need to neglect it. So see the remaining, which is the minimum distance is 3 3 4 4 3 3 4. So 3. So from the table we can clearly see that the minimum distance for the error correcting capability is 3. So substitute that 3 here. So 3 greater than or equal to S plus 1. So we can find S as less than or equal to 2. Then 2 errors can be detected. 2 errors can be detected is the error detecting capability. And we have another formula for finding correction capability. Correction capability is D minimum greater than or equal to 2t plus 1. So substitute D minimum, which is 3, 2t plus 1. So we'll be getting t as 1. So the error correcting capability of this problem is always 1. So only one error can be corrected. Next question we'll see. Prepare a suitable decoding table. So we will prepare a suitable decoding table by the formula H matrix. So H matrix is P transpose IQ, Q cross K. So how to find the H matrix? H matrix is your check matrix. Parity check matrix, we'll find it. So this parity check matrix can be obtained by just a minute. The H matrix can be obtained by this P matrix. P 111 110 101. So make transpose of that P. Here we have P. So this P, you make transpose of that. Write it as H. And then IQ is the identity matrix. Here we have the identity matrix 100 010 001. So take these two and prepare H. So on doing that, we will get this H transpose. I just skipped out of how to determine H and H transpose because I directly wrote H transpose, which is required for syndrome. So H you will get in this P transpose and IQ. So that taking that, I do H transpose of that. So I'll get this matrix. Okay. We'll be getting H transpose matrix as this. 111 in the first row, 110 in the second row, 101 in the third, 100 in the fourth, 010 in the fifth, 001 in the sixth. So now this H transpose is required for determining syndrome. Syndrome is S is equal to H transpose. Where is it? Syndrome is your S is equal to E H transpose. So now let us consider that there is error in the second bit. Let us consider that there is error in the second bit. Okay, this one. 10. We consider that error is present in the second bit. So in the second bit, in the error vector, write 1, remaining all 0. Remaining all 0. So do this operation S is equal to E H transpose. We get 0, 1, remaining all zeros into this H transpose. You do it, we get 110. And see that this is present in the second bit. This is present in the second bit. Consider the error vector size as the size of the received bits or the transmitted bits, and I take second bit as error. The second bit is error. I'll write the error bit sequence as 0, 1, 0, 0, 0, 0. So I do the modulo 2 addition of E and H transpose and check whether you're getting 110. You'll get obviously 110. And see this 110 which is obtained is present in the second bit sequence of H transpose. So we can directly write that second bit is being detected. The error in the second bit is detected, sorry. Error in the second bit is detected easily. If you do it for third bit, also it will detect. If you do it in the fourth bit, also it will detect. In any bits of errors that you make, There you need to put in that corresponding bit in error sequence and do modulo to addition with the H matrix. You'll be getting the corresponding row of H transpose as a syndrome. Okay. So this is how. This is the decoding table of that. For example, I show that in the error vector, I have it in the first row. In the first row, if it is error, you'll get 111. If it is error in the second row, you'll get 110 as syndrome. All these are in syndromes. If you use third vector, third bit as error, you'll be getting 101 of H transpose. If you say that fourth bit is error, so you'll be getting 100, which is fourth row of H transpose. If you say that it is in the fifth bit sequence, so I'll be getting 010, which is the fifth row of H transpose. If it is in the sixth bit is error, we get in syndrome 001, which is the sixth row of H transpose. So this is your decoding table. Okay, this is how to obtain decoding table. So any doubts in this decoding table? I'll give you 2 or 3 minutes for viewing this. You can check by doing modular to addition with the corresponding error bit sequence. And if the first bit is error bit sequence, write 1 remaining zeros. Second bit 1 remaining all zeros. If it is third bit to be as error remaining all zeros, and the corresponding syndrome will be obtained like this, which is always the corresponding row of H transpose. This is your decoding table. Let me check in the chat box for any questions. If there is any queries, put in the chat box. I'll give you some 3 or 4 minutes of time for seeing that, and put your queries in chat box. Okay, shall we proceed then? Okay. Thank you, Kishore. We'll proceed. So after finding the decoding table, the decoding table is obtained like this. After finding this, let us see what is the question. The question is, okay, fourth one, prepare a suitable decoding table. We are prepared. Next is to decode the received vectors. Decode received vectors are given in two different. One is 10 1100 and 000110. So make sure the bits of information of the received vectors is same as given with the relevant problem. So in the given problem we had seen C4, C5, C6. So which shows that there are 6 bits of information totally of X. So similarly, see in the received vectors whether there are 6. Count it one by one for both the received vectors. Just count one by one. So I had counted 2. Sorry, I had counted 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Both are having 6 each. Okay. So now write it. Write those two. One zero 1 1 0 0. Write it as it is. So since it is your received code vectors, so write it as y. So y is equal to 1 0 1 1 0 0. Now do what we are going to do is that we are going to do finding syndrome. So finding syndrome is S is equal to y h transpose. So simply write the y h transpose which you have found, write it as it is. And decoding this will result in an error. Decoding this will result in an error. So 1 0 1 1 0 0. You decode, sorry, you do modular 2 addition with h transpose, we get 1 1 0. So 1 1 0 is in the second. Okay, which is in the second. So this shows that the second bit is an error in the given y. Second bit is error in y. So we can write, note that 1 1 0 is in the second syndrome. So the corresponding error pattern will be 0 1 0 0 0 0. Now we can find the actual code word. So the actual code word can be found out by x is equal to y modulo 2 addition e. So y is this, it is 1 0 1 1 0 0, and e is this 0 1 0 0 0 0. So write it. Then find modulo 2 addition of these two, we get x. So this is your correct word. So here at the top it is written that 101100 is not standard code because there is an error in this. How do we find that there is an error in this? Is that by making YH transpose. If YH transpose is always 0, we don't get. If YH transpose is always 0, then we will not get any errors. Rather than that, YH transpose gives an error in the second row, which is second bit is errored. So if the second bit is errored, take that error, do modulo 2 addition with the given received code vector. Then we'll be getting the actual correct code word. So this is the procedure. This is how to find the correct code vector. Next, they are given another sequence. Let us check whether there is an error in that also. So decoding of 000110. So check whether there are 6 bits. Yeah, there are 6 bits. 000110. Okay, same I wrote. Now do the same procedure. S is equal to Y H transpose. I do Y 000110 with H transpose and I get 110. 110. So 110 is present in the second row. So the second row is this. So second row means second bit is error. So 01000 is your error vector. So error pattern is this. Write it. Y is this. Write it. Do modulo 2 addition to get the correct code word. So we get the correct code word as 0101110. So any doubts in this? Oh my. Okay, my battery is getting down. Let me put for charge. So any doubts in this problems in linear block codes? Any doubts in the above problems? Linear block codes. If you have doubts, put it in the chat box. And these are the references. So whatever we had seen in this linear block codes is just an introduction part to your cyclic codes. Why? Because the linear block codes are a systemic form where always the X having a message and check bits will occur in sequence. First, in the X vector, X code vector, we have message bits followed by check bits or checksums. Message followed by check bits. So whereas if you understand all these fundamentals like generator matrix, parity matrix, parity check matrix, code vectors, code words, weight of the code, decoding codes, syndrome, error correcting, and error detection and error correcting, Hamming distance. If all these topics are known, then only we can solve cyclic codes easily. Cyclic codes will be very much easier when you understand or when you are familiar with all these basic concepts. The unit 4 and unit 5 for your syllabus is very much big. So that's what. This is just the part 1 presentation. I'll give you 5 minutes time. You can have a glance. That's that. None of this outline. Outline is not comprised here. This is not the actual outline. Okay, forgot it. I'll delete it. This is the syllabus content of your unit 4 cyclic course. Okay. So in this presentation, which we had seen for the past 2 or 3 classes, is what I'm going to give you a recap. We had seen channel coding, different types of channel coding. The waveform coding, structural sequences are the 2 different types. Then we had seen 2 different error controlling mechanisms, which is used in data communication, followed by types of errors, random errors and burst errors. We had seen the basic terminologies of code word, block length, code rate and channel data rate. Definitions of code vectors, diagrammatic representation of the code vectors for n is equal to 3, which is 2 power 3. N is equal to 3, we get 2 power 3, which is 8-bit states. The Hamming distance, its capabilities to detect and correct, code efficiency, the different structural sequences. The structural sequences had 3 different types of codes: parity coding, block coding, convolutional codes. So again, the structural sequence can be classified into linear and non-linear. We had seen linear codes as an example in this presentation, blocking codes of linear type, linear block codes having n comma k in systematic nature. So this is your linear code definition. We had found C is equal to MP. Check bits, we had solved a problem for that. We had seen parity check matrix, how to obtain this. We had seen how to obtain Hamming codes, its error detection and correction capabilities. We had found how errors can be detected with a relevant example. P, G, C, M, P, and we had found code vectors also. Error detection and correction capability, and encoder of Hamming codes, how the encoders are present for Hamming codes. We had seen syndrome decoding. After encoding, we need to decode it. So in decoding, if both y and x are same, we don't get any errors. And if y and x are not same, we get errors. So how do we detect those errors? With a relevant example. Definitions of that, syndrome, how to calculate syndrome, how to use this syndrome for finding which bit is error, how to rectify that. And this syndrome decoding is useful only for a single bit error correction that we had seen. For multiple error corrections, we need to use extended versions of Hamming codes. Then we had seen a relevant problem, and we had seen syndrome decoder, how to draw the decoding circuit for a linear block codes. Then a problem on the systematic linear block code. So this is an outline of what we had done in this presentation. So any doubts you can put in chat box. Okay, thank you for this presentation. I'll start another presentation. Kindly await. I think hopefully you would have received the material for Unit 3 in your Google Classroom.
Ana bisa sampai ya, Bang.
In your Google Classroom, you can check the marks also for first assessment test. The same will be passed on to the examination section.
Dinesh,
The sir, good morning, sir.
good afternoon. How things are going?
Nice,
Hello?
sir.
How is it going? Now total,
Yes,
this
sir.
is the very less strength, is it?
Yes, sir.
Around 14 students only there, around 14, 13.
Yes, yes, sir.
What is the total?
Yes, sir. 19 is the strength, sir.
19, huh? 19.
Yes, sir. 19, sir.
Okay, okay. Any problem? Any problem?
No issues, sir.
Okay, okay, okay. Carry on, carry on, carry on.
Thank you, sir. So after the linear block codes, we'll be seeing a subclass of the linear block codes as cyclic codes. So the cyclic codes outline is that we'll be seeing the description of cyclic codes. Again, the generator G, parity check H of cyclic codes, how to encode a cyclic codes similar to our linear codes. Then how do we generate a Hamming codes for cyclic function, the same computation of syndrome and error as we had done for linear codes, then followed by decoding of cyclic codes and using the same cyclic codes for Hamming structures. Then we'll be using the same syndrome for error trapping and an improved version of the error trapping system by using trapping decoding systems, followed by 23,12 Gole codes, shortened cyclic codes, a type of cyclic codes which is used, and cyclic product codes, at last quasi-cyclic codes. Okay. So let us see what is this cyclic codes is first, because we had defined two different types of coding, channel codings. One is your waveform based, second one is systematic based. Sorry, structured sequence based. Under the structured sequence based, we are having three different, in that linear codes is an most prominently used codes. Under that we have this cyclic codes. Always the cyclic codes are in the form of systematic or non-systematic. So systematic is that, you all are familiar what is systematic is, that following the message will be having the check bits, which is systematic. And in non-systematic, it could be in any format. Either C can come in between M, or C can be in prefix of M, whatever might be. The different combinations of M and C to obtain X can be obtained in non-systematic form. So the cyclic codes are always a subclass of linear block codes. The cyclic codes can be represented in both systematic and non-systematic forms. In systematic forms, we know that we can separate the code vector or the check bits by putting a small notation between message and check bits as X is equal to M, a notation semicolon C. This is the form for systematic, where M represents the message bits and C represents the check bits. So M we calculate it from K, number of bits of K, and C we calculate from the number of bits of Q. So this is your cyclic code. So the definition of the cyclic code is that a linear code is called a cyclic code. A linear code is called as a cyclic code if every cyclic shift of the code vector, we'll see that what is that cyclic shift, either in the left hand side or in the right hand side, whatever might be. If every cyclic shift of the code vector produces some other code vector, if the every cyclic shift of the code vector produces some other code vector, then we call it as a cyclic codes. For example, if you have a code vector, for example 0, 1, 1, I do a cyclic shift of that. In right hand side 1 bit, I get 0, 0, 1. So this 0, 0, 1 should be present in the form of another code vector. If it is there, then we call it as a linear codes. So this cyclic codes has two properties. One is linearity property. So that we had seen what is a linear property in the linear block codes. The second property is your cyclic property. So let us see the first property first. So the linear property states that sum of two code vectors is also a valid code vector. Sum of the two code vectors is also a valid code vector if let us consider that I'll show you an example, don't worry. If I consider that x1 and x2 are two code vectors and I do linearity property of that, if I do linearity property of that, that will produce another code vector which is a valid one. Okay, if it is a valid one, then linearity property is satisfied. Okay, so the property stating that sum of any two code vectors is also a valid code vector. If I do x1 and x2 modulo 2 addition, I get x3. So that x3 should also be a valid code vector. Then it is called as linear. So next is the cyclic. So in so next is the cyclic property. In cyclic property, if we shift, there will be two types of shifting, either right hand side shifting or left hand side shifting. So when we do left hand side shifting, we call it as MSB shifting. When we do right hand side shifting, we call it as LSB shifting. So shifting the least significant bit and shifting the most significant bit. Okay, so when we do this shifting, it will produce another code vector. If that is the case, then it is a cyclic property. So every cyclic shift of the valid code vector produces another valid code vector. Hence the name cyclic is given to this. Okay, so hence the name cyclic is given. So for example, we take x is equal to xn1 x. So these are being represented in code vectors x. Now let us shift the above code vector to left hand side. Okay, left side shift. So one cyclic shift of x is given as x dash. X dash. So you can see that left hand side shifting is done. Okay, you can see that this in equation 3.4.1, the xn minus 1 is brought to the right side most. Okay, so this xn minus 2 will become MSB and this xn1 minus 1 will become LSB, least significant. So this is your shifting towards left. And if I do again one more cyclic shift, I do another one more cyclic shift, what will happen is that xn minus 3 will become your MSB and this xn minus 2 will become your LSB. So this is what, and it goes on, which can be represented in x double dash. If I do one more shift, cyclic shift, then xn minus 4 will be your x triple dash MSB and xn minus 3 will be your LSB of that. So this is what cyclic property is. We'll prove all these things also, don't worry. So the representation, I'll complete with this, then I'll take the attendance. Only the representation of code words. So the representation of code words is easily done by a polynomial. Why? Because the representation of this will be in the form of degrees. So polynomial of a degree can be easily represented here to indicate in which degree these are being present. So the code word can be represented by a polynomial of degrees less than or equal to n minus 1. So we can write x of p for the given transmitted code vector. The polynomial of the degree can be written as x of p is equal to xn minus 1. So as it is, polynomial of this is p n minus 1. For x of n minus 2 is p n minus 2. Then it goes on till for x of 1 it is p power 1. So we can write p. For x naught it is p power 0. So we write only x naught. So which is equation number 3.4.4. Here x of p is polynomial of degree n minus 1. P is the arbitrary value of the polynomial. Okay. And I give what is p n minus 1 is your MSB. P naught is your LSB. P1 is the second bit from LSB. P power 2 will be the third bit from LSB. P power 3 will be the fourth bit from LSB, and it goes on. Okay. So why to represent the codes in a polynomial would be your major question. So the answer is that there are two answers. Why do we represent the code words by a polynomial? Because these are algebraic codes. Polynomials are algebraic codes, and hence the operations such as addition, multiplication, division, subtraction will be very simpler. And the position of the bits, and we can represent the position of the bits with the help of powers of p in that particular polynomial. For example, if the bit is present in 0th place, p power 0. If it is in 1st place, p power 1. If it is 2nd place, p power 2. If it is 3rd place, p power 3. 4th place, p power 4. 5th place, p power 5, and so on. So the representation can be done as it is with the help of powers of p in a polynomial, such that the polynomial addition, multiplication, division, subtraction becomes very simple and easier. And we have done an example of this polynomial also in our introduction class to unit 3, I think so. Yeah. So kindly refer that. Okay. So remaining is generation of code words, code vectors in non-systematic. Okay. We'll see this in the next class. So kindly await for attendance. I'll check it. We'll see the remaining topics in the next class. So wait, I'll take the attendance. Is K Vamsi present? No. Okay. Sai Vamsi is present? No. Reddy Kumar is present? No, Reddy Kumar. Just wait, I am checking the attendance parallelly. Okay, Pavan Kalyan is always absent. Apart from that, no, Sai, Shrikar, Pavan. Pranit is there? E Pranit? Okay, E Pranit is absent. Okay, the absentees are Reddy Kumar, K. Vamsi, Pranith, Pavan Kalyan Reddy, and Sai Vamsi. So remaining all are present. So I had marked attendance for this. Okay. Then everyone can leave the meeting. Thank you all.